The third session of inverse modeling with prior uncertainty will be covering stochastic optimization. Why do we need yet another method? Well, in the previous session, we saw how we can do metropolis sampling as a way of solving inverse problems under Bayes rule. The problem there was that metropolis perhaps gave us too broad of a framework. It didn't specify what were good proposal distributions in doing that. What is the convergence? When do we stop, etc. So there's a need for good proposal distributions, in particular when you're doing spatial modeling. So what are proposal distributions when you're spatial modeling, in particular when you have geological rules and constraints that need to be honored? There's then also a need for an alternative to this rigorous MCMC sampling, because in practice this becomes very difficult to do, in particular in cases where you have lots of parameters, lots of different uncertainties, which is the case in most of the subsurface. We have uncertainty on the structural part, on the lithological part, on the petrophysical part, and the fluid part. We end up with hundreds of parameters, and so doing a metropolis sampling or Markov chain Monte Carlo becomes very difficult to do. So then the question is there something between Monte Carlo and Markov chain Monte Carlo? To understand that there's something in between that looks more like a stochastic optimization rather than a stochastic inversion, let's cover first what we are really doing when we're writing computer models. So when we're writing computer models or models, stochastic computer models, that means models that require at some point random numbers. And basically the computer code takes as input some kind of distribution model that we would like to draw samples from. The specifications, right? What is the function, for example, a normal function or Gaussian function, some mean, some variance. These are numbers that are specified, and we'd like to output some outcome realization or sample. So in order to do that, here in this case of multivariate distributions, we'll need many of these random numbers. So these random numbers are input into the computer code together with the model, and out comes a single realization or a single model. Before we explain a little bit how this all works, let's talk about generating pseudo-random numbers. So this has been around for a while. In fact, it was John von Neumann in 1946 who sort of basically developed Monte Carlo. And so he had a very simple method called the middle square method. I'm not using that today, but it just gives you an idea of how we could generate random numbers in a sort of totally random fashion. So he says take any number, square it, and then remove middle digits of the resulting random number. For example, then use that random number as a seed for the next iteration. So you'll see is that, first of all, you need to start with some kind of number, and that will be called a seed. And this seed will generate then a chain of realizations. For example, if we take the number 1, 1, 1, 1, we square it, we get the number 1, 2, 3, 4, 3, 2, 1. And put a 0 for that in front of it, and we have an 8-digit number, which we obtain from a 4-digit number. And then basically we take the middle part of it. So we got here, if I put on my pointer, we got here 2, 3, 4, 3. So that is 2, 3, 4, 3. So then we do and use the same idea over and over again. So that gives us a sequence. And the sequence can just be repeated exactly if we start exactly with the same seed, which in this case is 1, 1, 1. So that leads to some kind of periodicity, which we don't want. The most commonly used is a linear congruential generator. It's basically saying that we take again a seed. So the seed would be U0. We take that U0, multiply by some A, add some C, and then we'll calculate the remainder with division by M. And so that is now our next number in the sequence, and that provides us then with a series of random numbers. So the number U0 is that seed, and so there's often a major confusion of this seed, and sometimes we see analysis of putting the seed in a sensitivity analysis or making explanations around seed, and the whole point is not to do that. The seed has no meaning whatsoever in terms of its value of its parameter. It's just essentially just a key to unlocking a particular chain of random numbers. And so the nice thing about the seed is that if you come back the next day and use the same computer, it will generate the exact same random numbers. But otherwise, don't use the random seed at all in any kind of analysis. Okay. So what kind of a computer codes are we talking about? Remember we said that the a computer code. A stochastic model is essentially, a stochastic computer code is basically a deterministic function which receives some input and as well as a series of random numbers. So for example, here we have as input a covariance function, a mean, and a set of random numbers. So we can have a deterministic code that uses these covariance functions to calculate a covariance matrix. Say, for example, I want to simulate on this three-dimensional field. Then I take this spatial covariance, turn it into covariance matrix, and calculate the Cholesky decomposition to get the lower triangular matrix. And then we return as one realization here, y is simply the mean plus L transpose times the series of random numbers. So you see now very clearly what I meant in that first slide, which says it takes some input, it takes a series of random numbers, and it returns an output. So obviously, if you change u, then you change y. All the rest is fixed. So the question now is, how can we perturb this? We want to perturb this model. That's interesting. It may be for generating new proposal model in metropolis sampling. And in doing so, I just don't want to generate another random model. I generate something that's a perturbation of the previous model. So then you notice that we'd like our model, of course, to still have the same mean and the still covariance function. So the only option we have is essentially to perturb these random numbers. And so instead of generating just another chain of random numbers that gives me a different u, I will now do something different. The first idea there is to do what is called gradual deformation, a method that was developed by Lin Hu in 2000. And so this is really only for the Gaussian case. And in the Gaussian case, we are going to rely on a property. That's a very simple property. That is, if you have two random numbers that are Gaussian, so they're both standard Gaussian, V1 and V2, then any linear combination in this form with cosine theta and sine theta is again a standard Gaussian number. So the cosine and sine theta is simply that if I calculate the variance of this number, I need to square this, and I square that, and so I get the variance of this guy is 1 plus the square cosine square sine is 1 plus that is also 1, so end up at variance equal to 1, regardless of the value of theta. So if I can do that for standard Gaussian random numbers, then you can see that immediately I can also obtain the same result for uniform random numbers by just calculating the inverse of the Gaussian CDF. So if we apply that to the code in the previous case, and we're generating basically many values of theta, we can basically generate, as you see, a random, not random perturbation, but what are called gradual perturbations of this initial model into new models. And so, so that's something that's going to be useful, for example, for, as we see later, for stochastic optimization, as well as for generating proposals in your metropolis sampler. So here's then the code for the gradual deformation. So we state our computer code, which takes a set of random numbers as input. Then we initialize. We first draw from the standard normal distribution. From that, we calculate the corresponding uniform random numbers, and we set some kind of a stepping of our theta value, which is delta theta. So once I have V1, I need V2. So V2 is generated here in our iteration. And so then we're trying out various theta values until 2 pi, and each time we calculate a v theta using our equation, and we invert for the corresponding u theta, and we run our computer code again with u theta. So when I'm done with theta, you notice that I have to refresh my v here. So instead of having v1, v2, I'll need to have v2, v3. So I just assign the v1 to v2, and I generate the v3 here, and I keep on doing that. And that is basically an infinite loop that you can run and generate variations on your computer code. So that works really well in continuous cases. But what about in discrete cases, or any case of any kind of distribution could be a mixture of discrete and continuous? So in a discrete, of course, we can perturb random numbers, because the problem there is that we basically have only, say, 2 outcomes. It could be binary 0, 1. So I developed a method called probability perturbation. Instead of perturbing the random numbers, from which then using those to draw from probability distributions, what we do is we actually perturb the probability distributions themselves. And so a very general framework to perturb a probability distribution is shown over here. We can always write, so the theta has the same role as the cosine theta, sine theta as before. So here's my original distribution. So a slight perturbation of this distribution for some value of theta is written in this. And so theoretically, you could show, and show in the next slide an example, that a draw from this distribution is the same as a draw from that distribution. That means that all the properties of the draws that you do, such as mean variance, skewness, quantiles, whatever you like of that distribution, are not changing irrespective of the value of theta. So to illustrate that, how can we perturb the flipping of a coin? For example, if I flip a coin, it could be either head or tail. And so it seems like that's something you can perturb. But in fact, you can. If you just simply Monte Carlo on head and tail, and you're just drawing random numbers, check whether they're above or above or below 0.5, and then assign a head or a tail. And so we can keep doing that, and we get this sort of random sequence of heads and tails. So in order to understand how we can perturb this in a more gradual fashion, let's say that I define this indicator variable or discrete variable I as 1 if I have head, otherwise 0 if I have tail. So note that the probability of having head is called P, and is also the expected value of that binary variable. So now we notice that in order to perturb a discrete event, we're going to perturb this probability here. So in order to perturb this probability, I'm going to write this probability as a new probability, which is this probability that involves now the theta. And so what I have is, I have this probability with the theta, that is 1 minus theta times the outcome. So this outcome is just an outcome of this distribution, which could either be 1 and 0. So this value I is only 1 and 0, plus theta times my original distribution. So as you notice is that if theta is equal to 1, then this part doesn't exist, and this is simply equal to that other distribution. If theta, however, is 0, then this distribution is simply the outcome that I have currently, or a new outcome that I have. So, for example, if I say, if I have currently head, which is IS1, then imagine that I now take theta as 0.1, then the probability that I have here is 1 minus 0.1. I plug in the theta. The P here is 0.5, so I end up with 0.95. And so you see that this probability, because this here is 1, is essentially is close to 1, which is 0.95. So in my sequence, I'm very likely to draw again a head. So if I then start increasing theta, then of course this will decrease until at some point I'm drawing this randomly. And so this is what we then have in perturbation, is that you create a sequence of numbers that initially it's more likely to generate head, and as you go down and the theta changes, you're more going towards generating more tail values, etc. So of course we're not interested in just flipping one coin, we're interested in generating spatial models. And suppose here that I have generated a spatial model which has a discrete setting. I have something that's presence of something, something that's absence of something. Then if I take my theta very small here, that theta is RD, then you notice that I get a very small perturbation of this model. You see that this object here is slightly changed, this object is slightly changed, etc. When I start increasing theta, you notice I get increasingly bigger changes until theta is 1. I just get another model that's independently of the initial one. So you can apply that to whether you have continuous variables with binary, whether you have multi-category, or whether you have continuous models. You can apply this in all these cases. Okay, the probability perturbation then can also be written for particular cases of the uniform distribution. So we state our computer code, we have a uniform distribution on the parameters u. So this is just sampling those from the uniform distribution. Again, we set our delta theta. Then we draw another sample from the uniform distribution. And so then, while theta is less than 1, we apply our equation here. So remember, our equation looks very different from the gradual deformation. It looks like this. It has two components, which is the original distribution we'd like to draw from. In our case, this is a uniform distribution. And then we have this part here with the indicator function. So we have to do a test here, right? So if in order to draw from this V here, a V here, I need to check whether it's larger than V1. So I have two cases. The First case, if this is larger than V1, which is this case here, then essentially I get here a 1, and then plus theta here, the uniform distribution, which is that f of v here. And else it would simply this last part. So this is the way to draw perturbations from the uniform distributions that go between U1 and U2. So if I want to keep iterating on that, then I replace U1, U2 with U1, and I generate then here U3, and I apply this equation. Both gradual deformation and probability perturbation are methods of walking around in the sampling space, not in a random fashion, but more in an organized gradual fashion. The question now is, how can this be used for inverse modeling? To understand that, let's see where we have an inverse problem where we have calculated some kind of mismatch between the model and the data. So it's essentially I've ran forward simulations, and I can compare the observed data with the forward simulated models. So this is its RMSE here that we show. Now, what we now do, of course, is that our model realizations or perturbations are now parameterized to a one-dimensional parameter. This is essentially the sine theta or the theta that was used in the gradual deformation method and the probability perturbation method. So what we'll do is we'll start from some initial model, which is represented by, of course, a single uniform random vector, because every single model can be attached to a single uniform random vector. Then what we do is we have a second independent model drawn from the prior that requires, again, one of these uniform random vectors. And then what we do is we try to find by this deformation or by this probability perturbation, we try to find along this line essentially, or along in between A and these two here, where we do have the lowest RMSE. And that requires simply solving a one-dimensional optimization problem. And there are, of course, many methods for that, such as bisection, regular falsi, and so on. So once we have found that, then this becomes now our new initial model. So what we're doing is now this optimized, it's still a uniform random vector, but it is now optimized. And so we now draw another uniform random vector, which creates a new model, in this case, this model over here. And we can start now finding essentially by one-dimensional optimization our optimal point, and so on. Of course, at some point, we may not find an optimal one. So for example, if I go here between C and C here, I won't find anything because this is a higher likelihood point. And so then we just discard that one and we keep on searching. So the idea here is to turn a very complex high-dimensional optimization problem into a series of one-dimensional optimization problems. So this is very different from the Metropolis sampler. Metropolis sampler, we're trying to walk around in this space using a random walk. In probability perturbation or gradual deformation, we're solving an optimization problem. And so in order to find another solution, we have to restart our optimization problem. That means we start again from an initial random guess. Okay, let's look at an example. There are many examples of both methods that are published on real cases. And here I have an example of this website, the Waste Isolation Pilot Plant. And this is to do with nuclear waste. And so how do we store nuclear waste in the subsurface? In order to model those effects over the long term, of course, we'd like to know what the groundwater situation is there. So model the groundwater would require modeling the hydraulic conductivity of the system. I'd like to note also that there are methods of global gradual deformation and local gradual deformation, and so the same for probability perturbation. In a global deformation, we essentially, as we've shown before, we simply modify the entire realization. So here we see that we modified this entire realization into a new realization at 0. So if I do want to do local gradual deformation, then simply I only perturb the random numbers that have to do with this part, and I keep the random numbers that have to do with this part constant. So I still maintain all the properties of for example, the variogram, because if I take a random set of random numbers, add to that another set of random numbers, that union is also a set of random numbers. And so by doing that, you can see that only the area in the middle is really perturbed, and that's some property that we can use to our advantage. For example, if most of our data comes from this area and this area is, or we'd like to perturb, we'd like to perturb this area only while freezing this other zone is an interesting application. So here's a particular site. I'm not going to go too much into detail. I'd refer to the paper. But what we have here is we have several wells. This is essentially the area of interest. We have several wells. We measure transmissivity. We measure head at those locations. And so the question is, can we reconstruct the transmissivity given the head observations? So we also know that transmissivity is not just a random thing. It has also a certain spatial distribution, and that is modeled here through the variogram. So here see, for example, a kriging estimate of the transmissivity. So we see a high transmissivity here and low transmissivity over there. And so, of course, that kriging estimate, as you notice, gives you more heterogeneity where you have more data. And so in order to come up with a realistic transmissivity, we'd like to do stochastic simulations of transmissivity and constrain that to the particular head observations. Okay, so here are the results of that. So we started with this initial model. So we noticed that this initial model indeed has seems to have a realistic spatial variation. This is then, if you forward simulate that, this is then the head on the initial model. So we see that the head is higher here and lower there. So groundwater groundwater flow is going in this direction. So then I run my my probability perturbation or gradual deformation. In this case, is the gradual deformation method. And so you see here, as the number of flow simulations increases, we see that the RMSE is going down. And after a while, I get no more improvement. I get a low RMSE, and this would be then the model that is matching my observations. What you notice is that the variogram of this model and the variogram of that model, at least the residual variogram, is still the same. And so, in addition to matching the hydraulic head, we also are preserving the spatial distribution. And here is the resulting head for the matched model. For probability perturbation, there are also a number of real-world cases, and we'll talk here about an application to a North Sea reservoir. So here's a case with the North Sea. It's a case with, we notice here that we have gas on top, we have then oil, and then we have water at the bottom. So we have these various contacts. We have many wells that are already in production, and what is done here is that essentially we're injecting water into the aquifer and try to produce the oil that fashion. So we have injectors, which is called I here, and produces there. If we look at the stratigraphy, it's fairly simple. In fact, the porosity and permeability are not very varying in the system, but there's a problem related to the presence of calcite bodies. And so these are concretions that will have an impact on prediction, particularly when they're laterally continuous. And so these laterally continuous calcite bodies have been noticed to have a considerable impact on production. And we'll see that in the next slide, why that essentially is so. So here are these just some pictures of these calcite concretions. You can find them pretty much anywhere in the world. They're also outcropping at the ocean, often near the beach. And so we have these very strong calcareous deposits that may have a big impact on flow. How do we know that? Well, if we build just a porosity and permeability model using standard geostatistical methods, reproducing variograms and things like that, what we see is that we get complete mismatch in the production in particular wells. So the red here is the blue here is the actual production data, and the red is the simulated data. And so by perturbing this model, we're not going to get essentially a better match. And so what we need to do is add something to this model. That means adding these calcite concretions that are spatially distributed and have some kind of a certain extent. So the question is, where are the locations of these calcite concretions such that I can improve on this, on the matching of that model. So here, like before in the gradual deformation, we're not going to do a global perturbation of the model because we have many wells. It makes sense to do more local perturbations that are related to the production of that well. And so, for example, in the paper, what we do is we use streamline simulation to create these regions. And here are some ideas of how these regions are created. And I refer to the paper on the details of that is done. So that allows me essentially to optimize things per region. The papers also explain that the individual optimization does not destroy the spatial continuity That's simply, again, because we're using, again, uniform random numbers per each region. So if we add up all the regions, again, the union of all these uniform random numbers is still a set of uniform random numbers. So if you then run the probability perturbation, then we see indeed that we get this problem being solved, and we get a nice match to our observations in several wells. And at the same time, you notice that our initial model had this kind of spatial distribution, which was interpreted from essentially observations of analogs. So we have a certain extent of these calcite distributions that we notice, for example, here, that there is a lot of calcite concentrations around well P9 that were not in the initial model, and that led to the history matching of this production data. Okay, so let's wrap that up. These methods are quite interesting, but there's still considerable limitations. First of all, if you've noticed in the last two applications, we mostly dealt with spatial uncertainty. That means where the locations of certain features in space. What we did not deal with is uncertainty on global variables. And so, for example, you may have uncertainty on the groundwater gradient. You may have uncertainty on the proportion of these calcite bodies. Or if you're using variograms, you may have uncertainty on the variogram. So they were all fixed in those cases. And so this is a big issue. As I mentioned, also the joint uncertainty on static and dynamic variable. And of course, because you need multiple realizations, then each time in these methods, you have to start anew. So you have to start again with an initial random guess. Otherwise, you create too little uncertainty. So we have to do data avoiding over. We have to again run possibly several hundreds of flow simulations. And so you end up with possibly thousands of flow simulations. And so that makes it difficult to apply in certain cases. So in the next session, we'll talk about methods that circumvent these computational problems and just rely on naive Monte Carlo to solve the inverse problem.